Here we're going to talk about electrophilic aromatic substitution. It's a reaction of benzene, and there's a lot of details here. We're going to look at reactions of benzenes that don't have any other groups on them. Because once you put other substituents, or once you have a group on there already, the reactivity can change and the position where the reactions happen can change. But if we just start with benzene, the name electrophilic aromatic substitution is key here. It's a substitution, right? So in this case, we're going to take an electrophile, put it onto an aromatic ring, and replace something else. In this case, we're replacing a hydrogen atom that's already on benzene. And our overall reaction is just with some sort of electrophile. And it has to be a really strong electrophile. Right, something with a really strong positive charge in order to react, because benzene is aromatic and because it's so stable. So it's not easy to do these reactions. They can be slow unless you use a very reactant electrophiles. But from start to finish, essentially we're just adding something onto the ring. And there's a lot of different reaction conditions that can do these to substitute a bunch of different groups. Right? So if we react with bromine and iron bromide, that should be a 3 there. Those are bromination conditions. Right? We'll add a bromine. Similarly, chlorine. Right? Substitutes under these conditions with chlorine and iron trichloride. Concentrated nitric acid will give you a nitro group. Concentrated sulfuric will put a sulfonate. Right? So there's a lot of variety here, a lot of versatility. You can react and attach alkyl halides. Right? It's a way to put carbon-based R groups on there. And acyl halides will react as well. For a lot of variety. So a lot of different ways to do reactions with benzene and do substitutions. So there's a lot of variety here, but one of the key details is that it really does need a strong electrophile because of the aromaticity resonance stabilization of benzene. Just makes it very hard to react. So we'll do a very general mechanism here so we can look at, but all of these follow the same basic mechanism. Right? And that is one of the pi electrons, could be any, it's perfectly symmetrical here. First has to react with the electrophile. Again, this is going to be a very weak nucleophile due to that stabilization. Right, it's so strong that it just doesn't react with even a lot of the strong acids like HCl. So electrophile adds, it shows these pi electrons to react, so these two would stay, right? And then I've gotten rid of the pi bond, and the electrophile has to add to one of the two positions. We'll put it up here. And then to keep track of what's going on, of course, there's one hydrogen at each of these carbons around the benzene. We're going to draw in both of the affected hydrogens. Right? So if carbon on the top gained a new group, that's where the substitution happened, then the electrophile goes there. The carbon down on the bottom here has lost the pi electrons, but it just has the one hydrogen, so that's where the plus charge is going to be. It's going to be a carbocation. All right, so what happens at this point? So this is an electrophilic addition. This, we're set up with a carbocation. We've already done our substitution, so a reaction similar to what we'd see in E1, an elimination reaction can happen to reform our double bond. So some sort of base And what that is going to depend on the reaction conditions. You can take a hydrogen, so which one though, right? So if I remove this hydrogen here, right, which is already deficient, right, I gain the pi bond back, but then I'm going to be down one. It still isn't going to be quite right. Also, if I try and put the pi bond here, removing this hydrogen, that one is going to get in the way. That's going to be 5 carbons there. So the substitution is happening all on one atom here. The base is going to take the hydrogen where the electrophile was added, and then it's going to eliminate. All right, so this is the overall mechanism where first the electrophile adds, so the aromatic ring pi electrons act as a nucleophile. We get a carbocation intermediate here, and there wouldn't be any rearranging, but there would be a lot of resonance structures. So this is resonance stabilized, but no longer aromatic. So it has some stability due to all the electron sharing that can be done there, but it would be a lot more stable back as the aromatic ring. So aromaticity, if nothing else, is an unusually stable form of resonance. So we gain a lot of thermodynamic stability going back to the aromatic ring here. But we've got an electrophile addition and then an elimination step. And I forgot to draw my electrophile on my structure. Right? Then essentially we've done that substitution. Right? So there was a hydrogen here, now there's some other new group, and it could be any of these. But that's electrophilic aromatic substitution in general, and then there will be other videos to look at the more specific reactions.